welcome to the course Advanced Reaction Engineering. So, in this course we will discuss catalysis and catalytic reactors. So, there is data analysis that we will particularly discuss. So, in this course. So, here in the earlier case means in our last class we have discussed about various surface reaction steps, adsorption, surface reactions and desorptions, and based on that so we have derived some rate law or rate equations. So, that is by considering Langmuir-Hinseliud type of mechanisms we have considered, and one example also we have considered, and based on that three different rate equations by considering three different gases we have developed. Means if we consider surface adsorptions of the reactant is the rate limiting step or rate determining step. So, then one rate equations we can get, and second case is that if surface reactions is the rate limiting step, then another rate equations we can get by considering Langmuir-Hinseliud type mechanism. And third one is the case third, that is the desorptions of the product from the surface, that is the rate limiting step. So, considering that another or third rate equations we can get. So, from theoretically these three equations we can get. So, now once if we conduct that particular reactions, means experimentally you have to conduct the reactions by changing different reactant pressures. Means if there are two reactants, let us say one reactant concentrations or partial pressure remain the fixed, another one we can change or vary. So, by that way reactant if one or two are present in the reactions and product if there is there one or two product may be there. So, all these product concentrations, reactant concentration experimentally at a particular reactions conditions you have to find out, and based on that experimentally you have to find out the rate, and once we know those value, based on that we can fit the equations we have developed one by one. So, if either equation 1 is if it is fitted with the experimental result, then it is fine, then that initial guess was correct, and then we can consider that adsorption is the rate limiting step. If that does not fit, then the initial guess, that is the guess 1 adsorptions of the reactant that was we have considered as the rate determining steps, that was not correct. So, then we have to go for the second or surface reactions, that is the second guess, and with the experimental results that equations we have to validate. If it is not does not fit with the, if it is fitted then it is fine, then we can say that surface reactions was the rate determining steps, and that equations we can consider for that particular reaction. If that does not fit well, then we have to again neglect that once, and we have to consider desorptions is the rate determining steps, okay, and that rate equations we have to fit it well with the experimental results. If it is fitted well, so then we can say that desorptions is the rate determining steps for this particular reactions. If neither of those three reactions does not fit well with the experimental results, so then we can say that that particular model is not fitted well with this particular reactions, then we have to consider for some other reaction type of mechanisms. Okay. So, by that way means we have to consider different type of. So, here is Langmuir-Hinseliud type mechanism, Marx von Kraepelin type of mechanisms is also there. So, these are the things we can discuss today by considering one numerical problems. Okay. So, first we will develop Langmuir-Hinseliud type of models. So, how to develop that? So, there step by step I will discuss. First algebraic rate law we have to develop, that will be consistent with the experimental observations of the data, and then the rate law parameters you have to find out by using experimental data. Okay. So, here let us say this is our reactions toluene to benzene formations, hydrogenation reactions. If toluene plus hydrogens if you react in presence of any catalyst, then it can give hydrogens and toluene benzenes and methanes. Okay. So, here a packed bed reactors we have taken, see here catalyst we have filled, from the bottoms we can say toluenes and hydrogens as would be fit, and from the tops we can get benzenes and methanes, that are the product. These reactions we can conduct, and if we conduct these experiments, so what we have to do after conducting these experiments, experimental data we have to collect. So, here is the toluene and hydrogen, that are the reactants. So, this is the run 1, let us say run 1. So, if we set 1 atm toluene partial pressure, 1 atm hydrogen partial pressure. This is the initial conditions we have means set 1:1 toluene and hydrogens. So, once the reactions will take place, from here we can collect the products, we can analyze the concentrations, that is in terms of partial pressure of methanes, there is no benzene 0 partial pressure. Similarly, this was the another set means one set of conditions. Similarly, another runs also we can conduct there also this pressure 1:1 we can maintain. Here methane formations is 4 and partial pressure of benzene is 0, that way you are getting. Similarly, a number of runs you have to conduct by changing partial pressure of toluene and hydrogens. So, that data we can get. Okay, these tables you have to means first you have to experimentally you have to collect those data, means concentrations in terms of partial pressure of all 4 components, these tables you have to consider. So, after that experimentally by considering, or if we have this data, so rate we can find out corresponding. Okay. Once we know this, so this part is known, partial pressure of this are known. Okay. So, only these are the parameters are unknown for this particular reactions. So, rate law parameter evaluations means that we have to evaluate. So, this is non-linear equations, this is not these equations we can use, or by considering all those data, these are the things we have to evaluate, we have to fit it with the experimental data, and then one by one if we put these Kb and Kt. So, Kb and Kt we can put, so then the equations whatever it would come, that we can say that that is the rate equations for our this particular reactions. Okay. So, here's the data means collected from set 1, set 2, set 3, set D, this way means so many data was collected for this particular reactions. So, here's all those data, experimental data was collected, means once this partial pressure of all components were collected, then rate was evaluated from the differential rate equations we know. So, from there the rate we can evaluate. This table would be completed. Once this table is completed, then the 3 rate equation that we have collected or we have developed, one by ones we have to consider, we have to fit with this data. So, if any of these rate equations fitted with the experimental data, then we can consider that particular reactions is means rate equations is the rate determining steps, or that is the rate equation for this particular reactions. Okay. So, either this or this. Okay. So, these were developed I said, and then step 2 is the evaluations of the rate law parameters by using non-linear least square regressions programs we can use to find out this. So, once this K1, small k, Kb, Kb and Kt, these are the known parameters. So, now means if you want to do the reactor designs, there means rate equations we have to first find out, means whenever going to design a reactors, this rate equations is very important. From the experimental data we have to fit these equations, we have to develop or consider these reactions rate equations, there you have to fit it these equations with the experimental results. Once small k, Kb, Kt is known for this reactions. So, then we can say that let us say minus RT prime equals to K, let us say 0.01 partial pressure of hydrogen, partial pressure of toluene by 1 plus let us say this is 0.035 partial pressure of benzene plus this is let us say 0.3 into 10 to the minus 3 partial pressure of toluene. This is the rate equations, means this experimental data was fitted by using nonlinear regressions, and this is the rate equations let us say we are getting after fitting. So, now this is the rate equation for that particular reactions. Now, these equations we can use for that packed plate reactor design equations. So, what would be this minus Ra prime? So, that Ra primes we have to first develop by rate law parameters we have to find out. Once it is known, then these rate equations we can use for these reactions to find out conversions and weight. So, how changing the catalyst weight? the conversions will vary along the length of the reactors. Okay. So, this is ordinary differential equations. These differential equations you have to use by, or you have to solve by polymath. Okay. So, polymath chapters that how to solve ordinary differential equations, nonlinear equations, that we will discuss in our next class or some classes, how to solve this. So, that we will discuss. Okay. Means polymath program and ordinary differential equations, nonlinear equations by how to solve from the experimental data and rate equations, that we will discuss. Okay. So, now deducing rate law from the experimental data step by step. So, how we can do, means this part means this is experimental data and this is rate law. So, from here, so how we can find rate law parameters. Okay. So, experimental data initially means how to means rate law how to derive. So, from the experimental data you can see that means set 1 of data. So, here's methane's partial pressures, partial pressure of hydrogen and partial of toluene was that. So, then rate this way it is changes, means if partial pressure of methane changes 4 times, the rate significantly not changes, significant just slightly changes. So, we can say that rate law would vary inversely with methane conversions. Okay. So, if we vary partial pressures, it is significant, not significantly, but some changes is there. So, the pressures means a 4-fold increase in the pressure of the methane has a little effect on rate. So, methane is either a very weakly adsorbs or we can say this. Okay. So, now if we consider or see about the benzene concentrations, if it is changes 4-fold means 1 to 4, when benzene partial pressure in the reactions is this 1 to 4 time it changes. So, what would be the changes of the rates? Rate would be decrease. So, rate decreases with increasing concentration of the benzene. So, benzene concentration as a product if it is increased 4 times. So, then it has been observed that rate decrease. So, benzene partial pressure appears in denominator. So, benzene partial pressure and rate this way it would be. So, rate inversely proportional. So, if we increase the benzene concentration or partial pressure, rate would decrease. So, this way you can say. Okay. So, similarly in case of the toluenes and rate if we consider. So, here you can see the toluene partial pressure gradually increase, rate is also increase, means linearly it is changes, means rate and partial pressure of toluenes increases linearly. So, we can say that at low partial pressure of toluenes it increases linearly, means if we increase the partial pressure of the toluenes. So, then the rate of the reactions will linearly increase, directly proportional, but when high partial pressure we are going. So, there's you can see rate of the reactions decreased. Okay. So, this means based on that what we can say that rate of the reactions toluene concentration both the sides we can write denominator and here also. So, this way you can say that toluene concentrations this way it is varying. So, okay. And now hydrogen dependency on hydrogens. So, the rate law that we have to deduce. It is here you can see the hydrogen concentration it is linearly increased 1, 2 and 4. So, here rate is also linearly increased. So, here also we can see that the rate directly proportional to the partial pressure of hydrogens. So, then overall rate we can guess that this way it may be, means minus R A prime equal to K, means overall 4 components were there toluene, hydrogen, methane and benzene. So, considering that data or experimental data we can say that the rate may be like this. Okay. So, this way you can guess also, means we can deduce the rate law, means what would be, means rate law parameter, rate law constant later we can find out from the experimental results. So, this way you can say that how benzene concentration, methane concentration, hydrogen concentration or toluene concentrations related with the rate of the reactions, overall rate of the reactions. This is just a guess. Okay. So, this way you can guess that this way may be following. So, once overall rate equations and with the experimental data, this is experimental data, if we experimentally validate. So, then rate parameter, rate constant we can find out, we can say that these rate equations is fitted well with the experimental data, then you can consider these rate equations. But if it is does not fitted well, so then again we have to consider new rate equations until and unless we get a suitable rate equation that would be fitted with the experimental data. Okay. This is the trial and error way we can find a rate law for a particular reactions. Okay. So, Langmuir-Hinshelwood model is over. So, now we are going to discuss another type of rate equation, that is the Marx von Kraepelin type of mechanisms or rate expressions. Means for oxidation, this type of kinetics or rate equations usually valid for oxidation reactions. Okay. So, let us say any reactions, we can say this is the reactant cyclohexane, here oxygen in presence of any catalyst, we can, this is oxidized product, cyclohexanol formations is there. So, at the bottom of the reactors we can pass that cyclohexane oxygen, both the reactants, catalyst we can place here, and from the tops we can get product. So, here this is the oxidation reactions. So, in this type of reactions usually what we can see. So, this is reactants and the catalyst is oxide catalyst, both will take part in the reactions and then product formations is there, and this catalyst, whatever catalyst means, it is a oxide catalyst I had said. So, metal oxide, let us say nickel oxide. So, when reactions is there, so nickel metal formations is there, and that oxygens whatever, let us say here, so it is converted into this way, this oxygen is going there. So, metal oxide, this is the catalyst, they supplied lattice oxygens or oxygen to the reactant, means in this particular reactions molecular oxygens also we can use, but that molecular oxygen directly does not take part in the reactions or not reacting. So, here lattice oxygens of the reactants take part in the reactions formation of the product, and this is the step 1, and step 2 is that the metal oxide that was reduced nickel oxide to nickels. So, it further converted, means this is reactions 1, this is reaction 2, and reaction third means the reaction, this is the backward reactions, means these reactions and these reactions will take place simultaneously, and reverse reactions would be these molecular oxygens would be nickel oxide. Okay. These molecular oxygens react with nickel and again it is converted into nickel oxide. So, catalyst first supplied oxygen to the reactants and then it become reduced, and then these reduced sites react with molecular oxygens giving oxidized catalyst. The catalyst was at the beginning or initially was taken. So, these are the way the reactions we can see, or you can this type of mechanisms or this type of reactions we can say. So, this type of reactions we can develop say rate law equations, and we will validate with the experimental data to find out experimental reactions rate law parameters. Okay. So, let us say this is for this particular reactions. So, this is the experimental data that we can get, let us say for this particular reaction. So, now how to, here you can see, so the reactions these reactions how we can express from these reactions experimental data we are getting this, okay, partial pressure of individual components and product components. So, this way you can say, and corresponding rate also we are getting. So, this is run 1s, run 2, run 3 we are getting. Similarly, a number 20 run, 30 runs also we can develop for this particular reaction. So, here you can see reactions 1, that is the reactant converted into the product in presence of this catalyst, metal oxide catalyst. So, it is converted this oxide products, and the catalyst it remains like this, means these are the means green, you can say that green one, this is the oxygen atoms, and red one, that is the metal atom. So, here see you can see this is the vacancy, oxygen vacancy is there. So, when the reactions is completed, so this is the further reactions, means one reactions that is completed. So, product we are getting and reduced catalyst that was there. So, the catalyst partially get reduced when reactions is take place, and then this green you can see this is the lattice oxygens or oxygen atoms, this is the metals, and this is oxygen vacancy. Next step is that that catalyst regenerated. So, simultaneously in presence of molecular oxygen, the molecular oxygens we have taken are supplied with the reactants, This reactions means catalyst regeneration is there, again it would become the catalyst we have taken at the initially. So, this way the cyclic process will take place simultaneously. This type of kinetics is called Marx-von Kraplin's mechanisms. Okay. Marx-von Kraplin type of rate equations or rate expressions for usually oxidation reactions. Okay. So, for this particular reactions we will develop the rate equation, these rate equations we have to develop, and then with the experimental results is there, and this rate equation we have to validate, and rate law parameters that we have to evaluate, then that would be the complete rate equation for this particular reaction. So, how we can develop that? That we have to discuss. So, these are the initial guesses for this particular reactions, means two reactions are taking place simultaneously this way, that already have discussed. Okay. So, here few assumptions are there that are written, the reactions order first orders with respect to the reactants, and fractions of sites covered by oxygen, that is theta, and lattice oxygens that is at the surface are involved in the oxidation reactions in the step 1, and oxygen ions or atoms are assumed to exist on these sites, no reactants or no products theirs, and the surface rate of surface reoxidations by oxygen adsorptions and reoxidations of reduced sites. So, these are the 4 assumptions we can consider for this type of mechanisms or for this type of kinetics. So, based on that, this reaction 1 and reactions 2 we can propose. Okay. So, these are the 2 reactions we are proposing. Okay. So, here S is the lattice sites or active sites you can say. So, for rate expressions for this oxidations of the reactants. So, R we can write K1 partial pressure of R into theta 0, theta 0 is the vacant sites, fraction sites or lattice oxygen sites, lattice oxygen coverage or fractions of surface, this is, and this is the partial pressure of reactants. So, these are the surface sites concentrations we need and reactant concentrations we need, this way you can write rate. And for the second reactions we can write the rate is like this, rate of oxygens, rate of means disappearance of oxygens, this formations are in terms of plus we are writing. So, RO2 equals to K2 rate constant, partial pressure of oxygen to the power n, n we do not know, and then theta v is the fractions empty or vacant site that is present in the surface of the catalyst. So, occupy means oxygen and lattice oxygen coverage plus vacant site that equals to 1. So, means here you can see that this is the catalyst, this is means oxygen is present, here oxygen does not present. So, empty or vacant sites. So, this way you can say, so total sites equals to this plus this. Okay. So, all sites like this, fractional coverage of lattice oxygen and vacancy, okay, or vacant sites. So, now in this equations here you can say that the oxidation of 1 molecules of aromatic compounds or the R's required beta molecules of oxygens. So, both the rates, rate 1, rate 2, this is rate 2 we can write this way, means rate of reactions with oxygens and reactant molecules is like this, means if 1 moles of reactants react with 1 moles of oxygen, then beta would be 1, if it is means from the stoichiometry. So, beta we have to express, okay, means relative rates that we can say. So, beta component also we have to express or put here. So, then at steady state rate are equal. So, this rate and these rates we can substitute here, and both the rates are equals, and from there after rearranging, so or theta v we can substitute here, and then theta v in terms of 1 minus theta 0. So, we can write or express this equation this way. So, theta 0 we can get, theta 0 is the fraction of the surface or lattice oxygen coverage in the surface, that part we can substitute here in the equation 1. So, once we substitute this, the equations, rate equations would be like this, or we can write these equations same, both are same. Okay. So, rate equations for this type of mechanisms or for this considering this type of reactions is this. Okay. So, for this particular examples we take and we solve this. Okay. So, now deducing the rate law parameter from the experimental results. From the MV type of reactions we have developed rate law by considering the elementary steps. So, this is the rate law we have developed, and we have the rate means experimental data. This is our experimental data for this particular reaction. Rate we have and partial pressure of 3 components we have. So, how they are changes means if we change the partial pressures, how they will change means set 1 of the data, set 1, data 1, data 2, data point 3 we have minus R A partial pressure of hydrocarbons, partial pressure of oxygen that we have, okay, and partial pressure of oxide product. So, these are the things we have, means this rate also we have, these tables we have. So, now this is the nonlinear equations. So, using polymath nonlinear least square regressions programs, and this is the experimental data. Data or table this have, and theoretically we have developed this. Theoretically means by considering some mechanisms, reactions mechanisms. So, by MBK models type of reactions mechanism, so we have developed, let us say this is the rate equations. So, these equations you have to fit it with the experimental data by polymaths nonlinear regressions. Once we, this is rate is available and partial pressure, these are the components are available. So, you have to fit it well this, then K1 and K2 parameters will get. These are the unknown parameter K1 and K2 that we can get. So, once we know or this data is fitted well, so then we can say that the rate equation for this particular reactions is this. Okay. So, for example, so K1 value is this, K1 equals to, from the nonlinear regressions we are getting 0.02 K1, and K2 value we are getting 45. So, K1 and K2 value we can substitute here. So, then rate equations would become like this. So, from if it is fitted well, then only we can accept this. If it does not fit it, then we have to reject also this model. So, this is another type or MVK type of models that we have discussed, Langmuir-Hinshelwood type of models and MVK type models, and both the models how they are fitted with the experimental results and how to evaluate those experimental data to rate law by considering one by one's rate equations. So, this is MVK type models equations we have developed for this is the rate equations means for these reactions means toluene to benzene formations. Here we have considered Langmuir-Hinshelwood type of models, Langmuir-Hinshelwood, Haugen-Watson type of models we have developed for this particular reactions. We have developed rate equations and fitted with the experimental results, and then based on that we have developed some rate equations. Okay. This rate equation, let us say it is fitted with the that particular reactions. And another reactions or second reaction that we have considered, that is a cyclohexane to cyclohexanol productions. Here's MVK type of kinetics. Earlier one was the Langmuir-Hinshelwood Haugen-Watson type, and this is MVK type reaction kinetics for oxidation reactions we have considered, and with the experimental data we have fitted and we are getting this rate equations is fitted well with the experimental observations. Okay. So, then we can accept this rate equation for this particular reactions. Okay. So, I think two different type of models we have developed and validated with the experimental results and how to validate that. So, if it is nonlinear equations, then nonlinear regressions using polymaths or any other softwares we can use to get rate law parameters. So, that we have discussed. Okay. So, thank you. So, today is up to this. Okay. Thank you.